part of the education team. And part of the education work, we have the tutorials at the beginning of the week. Just before this, we had the TLS tutorial. And after the excitement of TLS, the excitement of Webrtc. We found the co-chairs of the Webrtc working group ready to guide us through the work and also show us some of the implementations that are going on. And without further ado, because we already lost some time, over to them. Here you go. Thanks so much. Oh, and very important, if you like this or if you do not like this, please fill out the survey so we can learn from you.
Thank you. Yo, whoa. All right. Yes, so I'm actually not one of the chairs. At least one of the chairs is sitting in this room, and I don't want them to get any ideas about me trying to take their spot. But my name is Dan Burnett. I am the first and longest running editor of the Webrtc specification in W3C. And I'm also co-author of the most popular book on Webrtc with Alan Johnston. So what you're seeing here is actually condensed down from an 8-hour live training class that we do. So the slides actually have a lot of information on them, and I'm going to do what I always hate when other people do. I'm not going to tell you everything that's on the slide, but I am going to tell you the important points on each slide, and you can read the details later yourself if you're interested. So these are not these are not the updated slides. Oh boy, it's just today. Okay, here we go. Real-time change. Yeah, these are the old slides. Sorry. Okay, so the main thing here is okay. So Webrtc is designed to do peer-to-peer communication, and this diagram, this Webrtc triangle, is the canonical architecture diagram for Webrtc. We have two browsers, a mobile browser on the left, a laptop browser on the right, and a web server up at the top. Now, just like with any web application, your browser is going to fetch the application from the web server and then execute it. What's different here with Webrtc is that the browsers are able to set up a media communication channel directly between the two browsers. Now, this is client to client. Okay, so this is actually a breaking of the web model with what Webrtc is letting us do. Now, in order to do this, to set it up, there needs to be some sort of communication between the two browsers before the media is set up. And for that, we use any kind of signaling approach you want, and I'll talk more about that later. In this particular example, I'm showing this one web server being used not just to serve up the HTML pages, but also to act as a relay for information between the two web browsers until they get the media connection set up. Now, just as an example, many of you may be familiar with SIP and may be familiar with the SIP trapezoid, which is kind of the canonical architecture there. You can do that with Webrtc as well. There's no requirement that you actually use the same application in both cases. There's no requirement that that your signaling goes through the same servers, and this is just showing that you can use multiple servers if that's something that that's important and works for you. So what's really being added, this is a very complex picture here, okay? But the main piece to look at is on the lower left corner where it says browser RTC function. It's that lighter blue there. There are new controls that have been built into web browsers now. There are new audio and video codecs, the ability to negotiate these peer-to-peer connections, and also echo cancellation and packet loss concealment. That's pretty cool, actually, that this is now in web browsers. Support for this is actually in all the major browsers today, except for Internet Explorer, and we'll talk more about that later. So Webrtc is cool because it uses the web platform. So you can write in HTML with JavaScript, and the standards are defined in terms of JavaScript APIs. Now, we're going to talk more later about that you don't have to use those APIs particularly. Webrtc also provides NAT traversal, and I will be talking about that quite a bit in a moment. And of course, the codecs that I mentioned. One of the nicest things is that it includes ICE, and that's one of the first things I'm going to be talking about. So, okay, for many of you who know networking, you're going to be just incredibly bored by this, okay? This is very high level. Let's say we have our mobile browser and our laptop browsers, and they want to communicate peer-to-peer over the internet, right? Media can go directly between those two. It doesn't have to be relayed to, you know, if I'm here and I'm talking with Alex, who's here in the front row, the media doesn't have to go all the way to the US and back, for example, okay? It can just go directly between the two of us. But as we all know, this is not really what the internet looks like. The internet actually looks like this, right? So the mobile browser on the left and the laptop browser down in the center, each of these is behind an access point, a Wi-Fi access point of some sort, a home, coffee shop, whatever, which has its own network address translation. So the problem with that is that, so I'm showing here the home case, and with the mobile browser, we've got two devices here with different IP addresses, but those are their private internal IP addresses. As far as anyone else on the internet is concerned, their IP address is the one you see at the top there, the 203.0.113.4, and not the 192.168 addresses. So stun is a protocol defined here in the IETF for basically being able to find out what your public IP address is. You send a query out to a stun server, and the response that comes back tells you what IP address it sees for you. Again, that's useful because these browsers are going to have to communicate with each other, so they need an address that they can route to. Now, there's another protocol that's related when you're talking about ICE, and that's turn. This is essentially a media relay. So this is the case where you've decided, oops, we actually do need to relay the media somewhere, hopefully not all the way to the US from here. But sometimes things just don't work peer-to-peer. The NATs and firewalls are just too restrictive for that to work. So the thing that's important here is that Webrtc includes support for this, okay? It includes support for ICE, which knows how to use stun and turn to find the optimal path if one exists. So Webrtc, and this is when I juggled the slides around, I actually put this one first, because for this crowd, I think this is probably the most interesting slide. Webrtc is a very highly successful joint standards effort between the Internet Engineering Task Force, us, and the World Wide Web Consortium, or W3C. So IETF is responsible for all the protocols, of course, and many of the protocols, actually virtually all of them, they already exist, okay? The intention was not to have to create a bunch of new stuff, but we have had to create extensions in the IETF, and I'll talk about a few of those later on. The RTC Web Working Group in the IETF is the one that has its main focus on Webrtc. I've listed some others here that are that have related activities as well. So anyway, it's spread throughout the IETF, or at least has been for the past few years. The JavaScript APIs are developed in W3C. And there are two groups there, the Webrtc Working Group and the Media Capture Task Force. So if you hear RTC Web, that's IETF. If you hear Webrtc, that's in W3C. And in general, when you hear people refer to Webrtc, in general, they're referring to the JavaScript APIs defined in W3C. Although what IETF does is rather important here as well. Just briefly on protocols, I'm not going to go through these in detail. These are all the protocols that end up getting used at some point and in some way with Webrtc. I do want to call out a couple of them. Let's see, I wonder if this will give me a pointer here. Yes, but you can't see it very well. The main thing I want to point out is that media is sent using SRTP, and that actually sits here basically, using DTLS for UDP packets. The data channel, which I'll talk more about later, uses SCTP and DTLS and UDP. These are the ICE-related protocols, like I mentioned before. And SDP, we'll talk about it a little bit more. This is used to describe exactly how the media is supposed to be encoded as it flows from one browser to another. So it's really interesting when I talk about WebRTC. It turns out that in every crowd, typically people either are communications people or they're web people. And it's tricky to create a tutorial for both because you actually need to understand some of both. So I'm going to talk now about what's new for web developers. There are two new API pieces. Again, this is in W3C. One is capturing of local media. So without a plugin, you can get access to the camera and microphone now. There are some extra specs that define how to get access to what's playing in a video element, and in fact, your screen and window as well. Another specification defines the peer connection, and that's a term you're going to hear a lot. A peer connection is what provides the ability to transport both media and data between two client browsers. You will often hear me say media peer-to-peer. It's media and data. So if you hear me say that, I'm in most cases referring to both. Okay, so very briefly, there are several steps here. This is not everything to building a WebRTC application. These are the pieces approximately in order that a JavaScript application would have to do in order to add in WebRTC functionality. Okay, and the first one is getting access to local media. That's done using the get user media call, and I'll show a little bit more specifics later. But one of the important things here is that this is where the user is asked for permission. I'm not going to cover the details on that, but I will show examples later on. When you call get user media, you're given a media stream which consists of one or more media stream tracks, and I'll give more details on these later. But basically, you need to have local media in order to send it. You need to set up a peer connection, and the RTC peer connection API is the one that does that. I've listed here all of the things that the peer connection actually does or provides an API surface for. So a lot of what we think of as WebRTC really lives here. Now, once you have a peer connection, that doesn't mean that any media is flowing yet. Okay? The simplest way to have media flow is to call add track. This is a peer connection call. And what it does is it basically tells the browser, I want you to negotiate how to send media. It doesn't actually cause media to be sent yet. You can also create a data channel as well at this point. Now, in order for the media to begin flowing, the two browsers have to agree on a lot of details, including which codecs to use, maybe some bandwidth information, candidate addresses, all of those kinds of things. And that's handled through the exchange of an offer answer, and I'm going to talk about this in a bit more detail. But the main thing you need to know right now is that there are functions for creating this session description, the offer and answer, and then functions for telling your browser what it is that you're actually using, which session description. One thing that I didn't show in this diagram is the signaling channel. And you'll hear me, I talked about this at the very beginning. The signaling channel is just however you communicate your low-level session description information before you have a peer connection going. So it's not standardized, okay? This is not officially part of WebRTC, but you cannot build an application without setting up some means for relaying this information from one browser to the other. Okay, so in a little bit more detail here, Navigator.mediadevices.getUserMedia is how you get access to cameras and microphones. And there is the permissions check. Now, once you have that media, there's a new method that was added to video and audio elements. This is interesting. We actually had to add this ourselves in the WebRTC specifications initially, but it then was moved into HTML itself. So the point here is that instead of just setting the source of a video element to be a URL, you can set the source object to be your media stream directly. Okay, so it's not going to fetch a resource that's at the that's referenced by URL. Instead, it's going to use a local media stream. You can also create new media streams as well. So just briefly, in the model that we have, of course you can load content from files or whatever, but what's really being added here is the ability locally to get access to the camera and microphone. Now, interestingly, the peer connection is actually both a source and a sink for media, because you can send media over a peer connection, in which case, when you're sending it, it's obviously a sink. When you're receiving it, it's a source. So here are a couple of examples of what the permissions prompt looks like. When you call get user media, you're going to be asked whether you're giving permission to use the camera and microphone, or in the case of Firefox, they tend to allow you to select which device you want to use. But in either case, once it's set up, both browsers allow you to change which device you're using if you have more than one. The key here is that you cannot use get user media without a permissions check at least once. There are conditions under which the browser is allowed to save that permission. I'm not going to go into it because there are some subtleties in that. But it's something that's important when you're building an application to keep in mind that at least the first time someone visits your site, they're going to have to agree to this permission prompt. Okay, so a media stream track, which we'll often just call a track, is a handle to one flow of one kind of media. Okay, so audio or video. A media stream is a collection of tracks, and the tracks do not all have to be of the same type. So you can have an audio to video, for example. One of the other things that's interesting about a media stream is that one of the intents of a media stream is that the collected tracks are to be kept synchronized to the best ability of the browser. And if you think about it, if you have a camera on a person and a microphone, you do want to make sure that the audio that's coming out matches the movement of their lips. Okay, so the browser works pretty hard to actually maintain that as much as possible. It's not possible to guarantee this in all cases, guarantee synchronization, because if your media came from, let's say, several different peer connections into your current browser, they may all have different clocks, and it's not clear exactly how you would synchronize them. But again, the browser will do what it can. Okay, so there's a lot in the peer connection APIs, as I said. There's some track items, which we've seen already, and there's some offer-answer controls as well. Oh, I wish I had the other slides. Okay. So I'm going to jump around just a little bit because I had reordered these. So I'll come back to this in a minute. I want to talk about SDP offer answer. So again, this is how do you get the information about which codecs to use, any bandwidth information, perhaps candidate addresses at which one browser can find the other browser. These things all live in something called SDP. We use the session description protocol, just as in SIP, or approximately as in SIP, to describe the media session at the protocol level. SDP is very widely used in SIP systems today. The use of SDP in the browser for WebRTC is defined in the JavaScript Session Establishment Protocol, and I had added a link to that in the other slides. Basically, if you search for that, you'll find the drafts that describe this. So with respect to WebRTC, this protocol level configuration information is just treated as a blob. Okay, it's not expected that the application, the JavaScript application, will ever have to look at it. So now let's just take a look at what the application does have to do, though. And yes, I'll come back to that other slide. So here we have our two browsers in the center, down here. And what we want to do is actually set up the peer connection and make it so that media can flow between the two. So this browser here, the one on the left, calls create offer and is given an SDP blob. So what this browser then does is it calls set local description with that offer. So what is returned here from create offer is an offer. It's this SDP blob. So the application needs to tell the browser, yes, this is what I'm using locally. But it has to do something else too. It is the job of the application to send this offer over the signaling channel to the other browser. And then the other browser takes the same thing. So this remote offer and local offer, they're the same. Okay, but from the perspective of this browser, it's the remote offer. So this browser calls set remote description. Excuse me, this code calls set remote description to tell the browser here, this is the description that the other guy is using. Now, once that's happened, this side can call create answer to generate the answer for this offer. And once the right side has the answer, which is right here, it calls set local description, just like this one did over here with the offer. This one's doing it with the answer. And then, just like before, the application is responsible for sending this answer over the signaling channel to the other browser, so it can call set remote description with that answer. And at that point, both browsers have the low-level protocol information that they need for media to begin flowing. Okay. So I just want to mention here that there are a number of extensions that were made to SDP in order for WebRTC to work. One is bundle. And actually, this is particularly interesting because as we worked on this, we found that basically everybody's been wanting to do this for a long time anyway. So before bundle, SDP only allowed you to send essentially one of your media lines, one of your audio or video streams to be sent over a single port. And bundle allows for these to be multiplexed together so that you can have one or only a small number of ports used for all of your media. There's an MSID specification that allows for the browser to signal what media stream the flows belong to. And then there's also additional information available about sources. So I've mentioned signaling a couple times. And I just want to point out that, again, you can do anything you want for this. This is not standardized in any way. So if you want to use WebSockets to communicate with a server, if you want to poll to a server, if you want to use a SIP library, whatever you want to do is fine. So I'm not going to read through all of these. You're welcome to take a look if you're interested in what some of the options are. But it's not standardized, but you have to do it. Here's one example, right? So if we're signaling using SIP, we've got some SIP library in JavaScript here. And so we have the web server as usual that the HTML application comes from. But then for the signaling, the library that we have is set up to contact a SIP proxy or registrar server just as you would normally for SIP. The only thing that's really different here is that the SIP signaling information is sent using the WebSocket protocol. And this is not a new RFC. That's one of the other things in the in the update. This has been around for a while now, but this RFC defines SIP transport over WebSockets. So this is what you would do if you have an existing SIP infrastructure and you just want to use the WebRTC front end, essentially. There are a variety of libraries that you can use to do that. Okay, briefly for audio, the browsers are required to implement both Opus and G711. Opus was developed here in the IETF. It's a great codec, sounds wonderful. G711 works. That's what I'll say about it. The browser is also expected to support DTMF, which are basically the events you get when you press the buttons on a keypad. For video, the requirements are H.264 and VP8. Of course, you can use anything else, right? These are the mandatory to implement ones. And in fact, people are already using 265 and VP9 for video. Opus is still the state of the art for audio. So just briefly, I want to talk about the data channel. Again, it uses SCTP. Basically, the data channel, we wanted to make sure that we had congestion and flow control for an arbitrary data channel. And so that's why we use SCTP on top of DTLS and UDP. I understand that some of the design of QUIC, or at least some of the motivation for how QUIC was designed, came from experience with building the data channel in WebRTC. So from a JavaScript standpoint, it's one of the peer connection APIs you call create data channel. And what you get back is something that has a send method and an on message. You can set an on message handler. By default, data channels are bidirectional, but you can change that. And you can send any string or any of the various array buffer types. So very briefly about security, there's a lot that could be said about this. Your media is always encrypted in WebRTC. We actually mandate the use of SRTP. This was a contentious point, but the world is used to it now. So just expect that. And this, I actually got rid of these slides because they're just very confusing. There is a mechanism now in the specification, an identity proxy mechanism, and essentially the SRTP is great because you know that your media is protected end-to-end from browser to browser. But how do you know that you're actually talking to the person you want to be talking with on the other end? Okay, the way WebRTC deals with this is by allowing you to use third-party identity services like Facebook Connect, for example, to log in to prove who you are. And basically, interaction with that proxy server is used to tie your identity in with the DTLS keys used for the communication. And so I don't want to say more than that about it. Again, I believe we'll have the newer slides up on there, and it's probably a little clearer in that. But just know that this is to help deal with that problem of wanting to make sure that the media is only usable by the person you want it to be used by and not just by the other browser. Okay, there are some new controls. New low-level controls in WebRTC. And going forward, we're eventually going to only be recommending the use of those. The reason I stuck it at the end here is because they're not implemented anywhere yet, even though the specification, assumes that everyone is implementing them today. So I'm going to walk through an example here. We have browser 1 and browser 2, Browser 1 has two streams in it. One that was defined within browser 1 and is being sent over a peer connection, and one that was defined in browser 2 that's being sent over a peer connection and received by browser 1, okay? Now, what I'm showing here is effectively what you see in the SDP. In SDP, there is an M line or a media line for each one of these bidirectional SRTP streams. So this shows media going to the right, this is media going to the left. Now, if you notice here in this first stream, stream 1, I've got audio, audio, and video. And for stream 2, I have audio, video, and video, right? So these are not symmetric here. So the question then is, since an M line can only have audio in one or both directions, or only video in one or both directions, how do you decide, which of these tracks goes into which of the M lines to make this work? Well, the browser tries to do smart things, but a number of developers have decided they don't trust the browser to do what they want them to do. And that's why we're getting some new controls. What's recently been added is RTC, RTP senders and RTC, RTP receivers, which we just call senders and receivers. And they are handles to the outbound and inbound RTP streams. So for every track that's sent or received over a peer connection, there's an associated sender or receiver. And that gives you direct access to those particular streams. So in the picture here, these are senders and these are senders. These are your receivers and these are your receivers. Okay, so it lets you find out, for example, you can get statistics on what's happening here. You can also perhaps control specifics if you have I'm just going to say specifics about how that particular flow is realized over your peer connection. Now, it turns out that wasn't enough, and that's because at the SDP level, every sender is paired with a receiver, right? So when you look here, there's something being sent and something being received. Now, of course, it's possible that it's only flowing in one direction and not in both. Well, with transceivers now, for each browser, there is now precisely one transceiver for each M line, and there's a sender and receiver for each of the transceivers. So, and I modified the diagram a little bit. It's actually each browser has a transceiver for each M line. So there would be 1, 2, 3, 4 transceivers that this browser has, and 4 that this browser has. And this transceiver has pointers to this sender and, well, this receiver, which doesn't have anything in it. Okay. Just briefly, the status of I want to talk about the status of the API. So again, the JavaScript APIs are being standardized in W3C. There are two main specifications, the Webrtc spec and the media capture and streams spec. Both of them are now at candidate recommendation stage. The Webrtc spec just went to candidate recommendation stage a couple weeks ago. So Webrtc, unfortunately, I've had this bullet up for a while when I give this presentation. Core is stable, just cleaning up edge cases now. So we're still cleaning up edge cases, even with it being at candidate recommendation. But we're getting close. What we really need is implementations. For the media capture and stream spec, yeah, it's been close for a long time. Again, we need some stuff implemented. For the IETF protocols, I'm not going to try to list all of them. Cullen Jennings maintains a dependencies draft. Which is always interesting to look at to see just how many specifications there are that Webrtc depends on. And then, of course, for the individual groups, you can follow their progress like you would normally. Just briefly, there are tools that have popped up, out in the world to help with Webrtc. There are a variety of libraries. I'm not going to list them here. I mentioned there are SIP signaling libraries. There are several of those. There are hosted signaling services. So if you don't want to write your own signaling, you can just use PubNub or Firebase or something else. Xerxes and Twilio provide hosted stun and turn services. So when you get to where you decide you need turn servers, and you will for virtually any application you're going to build, you need to figure out what to do, whether you want to put it up yourself or use one of these others. And then, of course, there's some interesting selective forwarding unit video servers and other, sort of optimization players in the space. There are also some higher level APIs. If you just don't want to code all of the stuff that you've seen, you can use some of these simpler APIs. Fun links. You can look those up on your own if you're interested. And I thought it'd be good to talk about this. I almost wanted to start with this one. Facebook Chat, Google Hangouts and Duo, and Amazon Mayday all use WebRTC. Virtually every unified communications platform today has WebRTC support. And then there are a bunch of free or freemium communication services that work. They really do work. I use them regularly when I go to contact people in my work. And that's my last slide. Now I'd like to have Alex Gouillard come up, and he will tell you what's actually really implemented and working today, assuming we can get the slides to come up.
All right. Thank you, Dan.
Maybe that means part one is my new version.
Yes.
Yeah.
The one you wish you had on screen.
Right. Right. So we're seeing that there's a part one and part two, and hopefully part one is my updated slides.
And, do I go full screen on that thing? No, to go full screen here.
There you go.
Doesn't help very much with that. Can you handle the slide change?
I can do it.
You know them, right? All right. Well, thank you, Dan. I think that was shorter than usual because I've seen this presentation during 8 hours done before. I think it's still very interesting, and it's very difficult to actually condense 6 years of work and multiple specification into 45 minutes. So you did a great job there. I'm going to try to do that in just one slide. So it's an even bigger challenge. And then I go through everything you said in the next 2 slides, right? Just to repeat everything. But first, my name is Alex Gouillard. I'm actually living and residing here in Singapore, and I'll participate in both the W3C and the IETF, mainly on WebRTC, but also on browser testing and tools, web drivers and things like that. Those who went to GSConf Asia last year already saw us. I hope you're going to enjoy having IETF in town. We know we're very happy it's here. So speaking about WebRTC, you have the 2 aspects. You have the JavaScript API, which most of the web developer are interested in. And then you have what is exchange on the wire, with, of course, is more of the scope of IETF and needs to work. So if you get a satellite picture of those specification, even though there are more than 20, the most important one are listed here. And the good news is all of them went into the latest stage of recommendation at W3C or are already a specification in IETF. I think that's the first IETF where we only need 1 session of RTC Web and not 2 as we used to. So that's great. That means consensus is reached for everything that is the specification, but that doesn't mean that the implementation actually is at the same level. So you went through the specification. Let's look a little bit about the implementation. During the lifetime of WebRTC, there was really 2 pivots. And for people that want to have all the gory details, there is a fantastic blog by the WebRTC Mozilla team that's going to give you in detail the list of all the SPI. So please go back to the slide later, take a look at that. That's really informative. That explains to you why today some websites use some kind of API, right? A set of API, and other use a different subset. So long story short, you can see 3 main stage, where at the beginning you were speaking about streams. So you could get a stream from your camera with audio and video inside, and you were passing a string, right? A stream, sorry. And then we went into a track model, where instead of saying, you know, I just want to stream, actually I would like to do track. So one use case that make us think like that was the webcam plus screen sharing. You know, I'm presenting a PowerPoint, I want to stream my PowerPoint, and I want to stream my face and my voice. Then I will need 2 video tracks and 1 audio track. And that was getting complicated with the Stream API, among other things that were complicated with the Stream API. Another use case, very simple, I'm using a mobile, and I want to switch during a call between the front camera and the back camera, right? This video is the same type, might be not the same resolution, but there is no reason why it would be complicated. And so we came with a replace track API that was specifically dedicated to that use case when you want to switch to 2 tracks of the same type, in that case, the video type, while keeping the rest, without going through an entire cutting the call, renegotiating the call, and restarting the call. Eventually, we brought in a more fine-grained API like that, and we wanted to make the glue with the SDP and all the exchange format. We were using the signaling format at that time, and that's where the transceiver came. And transceiver has a lot of very good application, not those that you're going to see directly in an application you're going to write yourself. There's not a lot of new API, but it will allow, for example, for a call to successfully go through in 1/10 of the time it took, right? So we call that click to first media. When you click accept the call button, how long does it take before you're actually in the call and start talking with someone? With the original version, that will be 1 to 2 seconds with full eyes. Then we bring trickle eyes. We bring that down to 100 something milliseconds. With the things that add transceiver and the new API will bring in, you will be able to go close to the experience you get with a real phone call today, which is ultimately what we want. There is no difference between a call over the internet and a call with a real telephone line. No difference between voice and audio, right? So if you look at those 3 generations, not all the browsers are equally advanced. And of course, the specification was still in flux. So if we go to the next slide, we can see what was presented by Chrome last week. So last week was the technical plenary meeting of W3C. Dan and I had the joy to participate there and flew in this morning. And Chrome presented that slide, which is, as far as we know, the latest state-of-the-art status of WebRTC implementation in Chrome. So get stack, track constraint, receiver. So part of the 2nd generation of the API are here, but not all of it. So the sender, which is the pender of the receiver, add track, on track, and so on, is still to be expected in a few revisions. Lastly, Unify Plan, which is the standard way of doing simulcast, a good way to actually adapt the resolution in case of bad bandwidth or a lot of people joining a call, is still using Plan B, an old version in Chrome, and it's blocking a little bit the standardization effort where Firefox is already, for example, using the real Unify Plan. According to Chrome, that should be completed by the end of this year or first quarter next year. On Firefox, it's a little bit simpler. Everything is there except transceiver, and I think Niels just told me last week or today that transceiver should be here within 2 weeks. So in terms of JavaScript API, you're more complete and more compliant today with Firefox than you are with Chrome, but it doesn't matter. It's going to converge in a very short period of time. Safari is interesting. Safari was a little bit late to the party, but that gave us an advantage. They didn't have any historical implementation of WebRTC based on the older spec. So they directly went for the latest version of the spec. So they directly went into the track and not the stream generation of the API. Unfortunately, they based on the Google code, so it was too complicated to switch to Unify Plan, and they're still using Plan B. There are a few other things that are still improvable because they are the latest implementation of WebRTC. But 1 year ago, Safari was not supporting WebRTC. So today we have all the major browsers that support WebRTC, including Safari on iOS, and that's really a big step forward, right? Edge, well, it's difficult to answer for Microsoft. They have different approach depending on the product and who you ask to. There's one thing we know for sure, Internet Explorer will never get WebRTC. They want people to move away from all the old Windows and get into Windows 10, so they're putting all the latest API on Edge. They think that if they put the WebRTC API in Internet Explorer, that will not give enough incentive from people to move away from Windows 7. Edge has two implementations today. One is based on ORTC with a polyfill on top, and another one that is the WebRTC 1.0, but first generation, which is the add stream and remove stream implementation. And finally, they have a third implementation for native that supports WebRTC and is, as far as we know, Bernard told me last week, the most advanced with support for VP9 and things like that, for example. So originally, the biggest problem with Edge was that they were only supporting a very proprietary codec called H.264UC. That was the SVC flavor of 264 used by Skype. Now it's getting much better. H.264, the vanilla H.264 is in. VP8 as well. VP9 with SVC is coming in some of the those 3 different stacks they have at Microsoft. So here again, slowly, by the end of the year, things will be interoperable enough. So you can initiate a call with Edge and receive a call from any other browser with at least one codec that will be understood by each side. So W3C, unlike IETF, require that test exists before you can become a standard. So we had compliance test, which is test of the JavaScript API. And that's very interesting for web developer because you can check if not only the API exists, but she behaves according to the spec or not. And so we were not close to consensus last year. So not a lot of tests were written, and they were written mainly by people that were volunteering their time. Harold over there, myself, and someone called Dominic from the W3C, were basically the 3 weekend contributors when our wife was not around. Now we put some more people. Google put a big focus on testing this year, and the result is we got 1,000 more tests. But beyond that, next slide. What's interesting is not the number of tests themselves, but the coverage. Only 10% of the spec was really tested 1 year ago, and nowadays, last week we did another check, and we went to 70%. So we went from 10 to 70%, all thanks to effort from people here in Singapore working on those specs. Next slide. Again, what does that mean if you're a web developer? Well, if I'm a web developer, I have 2 choices. I can look at the spec, they're beautiful. I really want what the spec is selling, but the implementation in a browser is not there. So I need to make a practical choice. And that's where things like jQuery came in. And that's where some polyfill and some adapters are also coming for WebRTC. So if you had to choose between the browser you look for, you could use those test suites to see which one is the most compliant. So in June 2017, Safari was the most compliant. Oh my God, that was a shock for Firefox. Well, they were not the most compliant by a lot, and still 50% of the tests were failing. Right? So those tests are very fine granularity, and you have to take them into account. I think the presentation we did before in terms of 3rd or 2nd generation and where they are is giving you a better idea. So Firefox is great at getting the latest thing in. They have almost everything there. You want to test the latest thing, test it against Firefox. Chrome and Safari are not far away behind, and you can expect everything to stabilize by Q1 2018. And I know you heard that before, but before the specs were still in flux. Now they're in candidate recommendation, which means there will not be any change in the APIs or in the object that you can use in the browser. So the only difference now is whether they implement it or not, right? So that's the situation as of today. To be able to test and to make the things better, the browser vendors, beyond the usual JavaScript testing, are also implementing the new test tools, especially one Kite that was developed here in Singapore for all the browser vendors to actually test specifically Webrtc in the cases where having only one browser at a time is not enough. Nowadays, the JavaScript API is pretty okay. Everybody knows what they need to do to make it work. But what doesn't work is when many people try to connect to each other, right? Edge try to connect to Safari in the same call with someone on Chrome on different operating system. That's not something we had the tool as a standard committee to test before, and we didn't have a lot of visibility in that, and that's where we were getting most tickets from the users. So now we developed a specific tool for that. That is going to be run every day to test interoperability between the matrices of different browser, revision, operating system, and so on. So we hope that this is going to reduce the number of problems you people might have experience is using Webrtc in big production environment, and that's really a big push by all the browser vendors. Again, specifically for IETF, they love to have feedback on the tutorial. Did that show everything you wanted to see? Did that leave out something you would have liked to see? Do not hesitate to participate, whether you're happy or unhappy about the results.
And I'll say that we're officially at time. There were obviously some technical problems getting started, so I think if I don't believe there's any other session that's right up against us right now, so we could take one or two questions. Any questions? Okay. All right. Thank you.
Thank you.